Good afternoon. This is Manoranjan Kumar, an assistant professor in Agriculture Department of Suresh Gyan Vihar University. So today in this video lecture, we will discuss about the design of drip irrigation system. In the last class, we have seen the different component of drip irrigation system. Uh, Mainly, there are three units. One is the head unit, other one is the pipe network, and third one is the emitting system. So how these components are designed, how these components are designed for a particular field. Okay, so in this topic we will see how the design of a drip irrigation system is accomplished. Okay, so to at the end of this lecture, the students will be able to know the different design criteria which affect the drip design, and also we will see the different steps to be followed for designing of the drip irrigation system, and also we will see the weighting pattern of drip emitter because weighting pattern play a very important role in drip irrigation design. So we will keep focus on this weighting pattern. For this topic, the students can refer these books. First book is Practical Manual on Soil and Water Conservation Engineering, written by Manoranjan Kumar and Angelo Francis Dennis. This book is available on Amazon.com. The second book, that is Irrigation Theory and Practice, written by Michael A.M. Or students can refer Keller, Jack, and Bristol book, Sprinkler and River Irrigation. And also, this is also a one good book, Efficient Use of Irrigation Water, written by G.H. Sankara Reddy and T. Elmanda Reddy. So these are the books which the students can refer for this topic. So let us start with this design of drip irrigation system. So first, we will see what are the important design criteria which affect the drip irrigation system efficiency. So these are the some design criteria: efficiency of filtration. Filter is one good part. In the last class, we have seen the filter is one of the most important part for the drip irrigation system. If filter is not there, then the life of this drip irrigation system is very low. Okay, so what is the efficiency of this filter? We will this play an important role in designing of drip irrigation system. Second is the permissible variation of pressure head. What is the up to how much uh, we can change the pressure? What is the how much we can change the pressure and what are its effect on the discharge of emitter? So we will study what is the permissible variation of pressure head. This also play an the important this is one of the main design criteria for duplication system efficiency. Other one is the base operating pressure to be used, degree of control of flow or pressure, a relationship between discharge and pressure at the pump supplying water to the system. This is also one criteria. Other one is the chemical treatment to dissolve or prevent mineral deposit, use of secondary safety screening, incorporation of flow monitoring. These are the important design criteria for which affect the drip irrigation system efficiency. Now we will see the design of drip irrigation system. So the different steps in designing of drip irrigation system. So these are the steps which can be followed by the designer to design any field for the drip irrigation system. First one is inventory of the resources and data collection, compu- computation of peak water requirement. Okay, third step is to decide the appropriate layout of the drip irrigation system. Fourth one is selection of emitter. Fifth one is hydraulic design of the system in terms of lateral, submain, and main. Sixth one is horsepower requirement of the pump. Okay, so first is the inventory of the resources and data collection. Before starting off, hello, So first one is the inventory of the resources and data collection. So before making a design, we should collect all the data related to this design. Okay, what are the different data are required for the designing of drip irrigation system? These are the important data. First is the water resources. What is the quantity of the water resources, stream size, volume, and duration for which the supply is available, and also what is the quality of water. Quality of water is also we should know the type of the water resources, where it is bore well or where it is tube well, where it is open dug well or where it is reservoir, pond, tank, or river, and location of the water resources. Okay, so we should know before designing a drip irrigation system which type of water resources is available, whether it is open water source or whether it is closed water source. Okay, if it is open water source, then different types of filter is applicable. If there is closed water source, then different types of emitter is filter is applicable. So for this filter, we should know the um, type of the water resources, and also we should know the location of the water resources. Means in the field or outside of the field, where is the exact location of the water resources? Where is the exact location of uh, open well or tube well? Okay, so that we can determine the exact length of the pipe. Okay, so this is the first step, first data inventory of the resources data collection. Second is the land resources. Okay, so in the land resources, we should know what is the size and what is the shape of the area to be irrigated, and soil type for its texture and irrigation properties like field capacity, wilting point, bulk density, allowable depletion level, including infiltration rate, etc., or topography of the land. Okay. So this is the third one. We should know, we should collect the data about the climate in that area, the climatic data required for the computation of crop water requirement. Fourth one is crop. Which type of crops the farmer wants to grow? What is the crop, the type of the crop? Okay, what is the sowing period or planting period and harvesting period of that crop? We should know this data. Crop coefficient. What is the crop coefficient for particular crop? Okay, fertilizer. This crop coefficient is required for the determination of the plant water requirement. Okay, because peak water requirement is very important when you make a design. Fertilizer requirement, crop geometry. So these are the same data which you should require before designing the drip irrigation system. Now, second step after the collecting all the data, the second step is to compute the peak water requirement. Water requirement means this water requirement is uh, the plant at different stages require the different water quantity. If the plant is small, then it will require the less quantity of water. If the plant is young, then it will require some more quantity of water. So after, sometimes the water required by the plant is highest. Okay, so that highest water required by the plant is known as the peak water requirement. Okay, and when we design the drip irrigation system, then this peak water requirement is considered for the designing. Okay. So it is the highest water required for the plant throughout its life cycle. Peak water requirement may vary depending upon the soil type, agroclimatic condition, and crop variety. This peak water requirement you can calculate by the equation, PET, potential area for transpiration, into Kc, is crop coefficient, area allotted to a plant. Okay, means row to row spacing or plant to plant spacing, that will give the area. Canopy factor. Okay, how much the shadow of the plant is there on the soil surface, that is the canopy factor. Irrigation efficiency. Okay, so in this way you can calculate the peak water requirement and you can use this data for the designing of drip irrigation system. So this peak water requirement can be expressed in mm per day or liter per day. Okay. So in this equation, there is a PET. How you can calculate this PET, potential evapotranspiration, by this equation? Potential evapotranspiration is equal to evaporation into fan coefficient. And generally, this fan coefficient is taken as 0.7. Now, the further step to lay out the drip irrigation system means layout means in the field where you should install the drip main line, whether where will be the head unit, where is the um, uh, sub main, where is the in which direction you can keep the lateral direction. Okay, so all this comes under the layout of the drip irrigation system. Okay. So it is possible to apply water to the whole field by drip irrigation method at the same time. However, this may result in the requirement of high discharge, which may not be available. Further, large diameter of main line or sub-main line, which could make the system more expensive. Okay, if the diameter of the pipe is increased, then your cost will also increase. So you have to keep your design should not be so much costly. Okay, and the high capacity of the filtration and filter unit. So we should keep this in the mind. Hence, the whole field needs to be divided in the convenient number of subunits. Each subunit is then designed separately and operated separately by having valve at the head of the subunit. In each subunit, we will keep one valve separately. Okay, so that other subunit cannot be affected. When one is in operating condition, then other subunit may not be affected. Now calculation of application rate. Okay, so application rate means in particular hour how much depth of water is going inside the soil. That is the application rate. Okay, and this application rate is calculated by this equation: drip discharge in LPH, number of laterals per row, dripper spacing, row spacing, or the other formula to calculate the application rate is total flow of entire field divided by total area. Okay. So unit of this application rate is mm per hour. Okay. The second formula is irrigation time. Okay. Means up to how much time you have to operate the drip irrigation system to reach its peak water requirement. That is the irrigation time. And you can calculate the irrigation time by this equation: peak water requirement divided by application rate, where peak water requirement is in mm per day or application rate is in mm per hour. Okay. Now, how many sub-units should be there in the field? So you can calculate by this total available time per day. कितना टाइम अवेलेबल है एक दिन में. Okay, time means in some area uh, the irrigation, the electricity available for 5 hours. In some area, it may be available for the 6 hours. Okay, so depending upon the area, depending upon the electricity availability, the total available time is there. Okay. So total available time per day divided by irrigation time per shift. In one shift, how much irrigation time is there? Okay. If the plant is small, then in that condition the irrigation time will be less. But when this plant will grow, when this plant will be younger, then that irrigation time will be more. Okay. So in this way you can calculate the irrigation time per shift. So this layout of the micro irrigation system, that is arrangement of main, submain and lateral, is done considering the shape, size and slope of the field. As as far as possible, the submain should run along the slope of the field, not across the slope of the field. The submain should run along the slope of the field and lateral should be laid across the slope or along the contour line. Okay. These are the different layout of the field is shown. Okay, just for reference purpose. Okay. This is the main line, this is the lateral. Here, this is the main line, this is the submain, and At both sides of the segment, there will be lateral. Okay. So in this way, different layouts are there. Now, selection of emitter. How you can select any particular emitter for any type of field. So if there is clay soil in the field, then in the clay soil, in the clay soil, the emitter discharge should be less in comparison to the sandy soil. Okay, because the permeability of clay soil is less. So when you deliver water to the clay soil, then for the some time the water will remain present on the soil. Okay, so if you are applying the high discharge emitter on the clay soil, then more water will be remain present on that clay soil. So what happens? The evaporation may take place. Okay, so evaporation may take place. This is nothing but this is the loss of water. So that's why we should choose the less emitter discharge when there is clay soil. And when there is sandy soil, then in that condition you can choose the high emitter discharge. Okay? So in clay soil, the clay soil absorbs water slowly and runoff can occur if water is applied too quickly. Clay soil will hold water very low and can stay wet for several days. Emitter discharge should be less, around 2 lph, and a spacing tend to be the further apart. Okay. So if there is clay soil, then you should keep the spacing between the emitter more in comparison to the sandy soil. In the sandy soil, we keep the spacing between emitter less. Okay, so that you can get the desired wetting pattern of that emitter. Okay. In sandy soil, the sandy soil absorbs water very quickly and runoff usually doesn't occur. Sandy soils do not hold the water very well and can dry out very quickly. Emitter discharge should be more, around 4 to 8 lph in sandy soil, and spacing tend to be close together. Okay, so that you can get the efficient that wetting pattern. In loamy soil, the loam soils are an ideal in between mix of clay and sand soil. Its absorption rate is greater than that of clay soil, but not as fast as sandy soil. Okay. So drip emitters of 2 to 4 lph are selected for planting in loamy soil. Okay. So if there is the main point is that if there is clay soil, then we have to choose the less emitter discharge. If there is sandy soil, then we have to choose the more emitter discharge. And also in clay soil, the spacing between the emitters should be kept more, whereas in sandy soil we should keep the spacing between the emitters very close. Okay, so this is the main point for the selection of emitter. The selection of emitter depends on the following parameters. First, depending on the soil, the discharge of the emitter should be less than the infiltration rate of the soil. If the discharge of the emitter is more than infiltration rate of the soil, then what happens? If the discharge of emitter is more than the infiltration rate of the soil, then in that condition, the runoff will take place. And if runoff is takes place, then some soil erosion may take place. Okay, so there are two laws. One is the water will be wasted, okay, and also the soil loss will be there. Okay, so we should select the emitter. That's why so that the emitter infiltration rate should be more than the emitter discharge. Okay. So soil type also governs the spacing between emitter. Heavy the soil, the more could be the spacing. Like clay soil. Clay soil, heavy soil, so spacing should be more. Crop. So in which type of emitter we should apply? In case of row crop, emitter need to be spaced so as to get the entire strip of the row. In case of close growing crop, and row crop, inline like a vegetable, inline and integrated emitter. Integrated emitter is nothing but it is one type of inline emitter in which the emitter is fixed inside the lateral. Okay, so inline or integrated emitters are preferred, whereas for the plantation or orchard, online emitters are preferred. Online is a tailor-made emitter, okay, and integrated is factory-made emitter. Okay, from the factory, this integrated emitter has been already has been come. Okay, now the single exit emitters are used for the row crops, while multi-exit emitters are suitable for plantation crops. Here, the different arrangement of emitter along the lateral is shown. Here you can say this is the lateral and this is the dripper, and this is the plant. So near the plant, one emitter is there, and here you can see this is the paired row. This is the one dripper plant. This is the paired row. So what is there in the paired row? Here you can see, and this is the one lateral, and this one is the other lateral. Okay, and on that lateral there is an emitter on a specified distance. These are the sorry. Yes, these are the emitters, and this is the star is the plant. Okay, so this is a pair row. One lateral will deliver water uh, to plant. Okay, this is a pair row. Now there is a two dripper per plant. Here this is the plant, and these are the two emitters. Okay, this is the lateral. There are three drippers per plant. Here is the one plant is there, and this is the lateral. Okay, and these are the drippers. One dripper, two dripper, and through one micro tube. Here one tube is there, plastic tube is there, which you can fix on this main lateral. And at the end of this micro tube, you can connect the other dripper. So this is the three drippers per plant. Okay, so in this type of exercise can give the more wetting pattern. Okay, now here this is the four dripper per plant. Okay, this is a six dripper per plant. So in this way you can arrange the dripper on the lateral. Okay, now third is the topography. Okay, so non-pressure compensating emitter could be used for relatively flat land, whereas on the land with eroding or uneven topography, pressure compensating emitters are preferable. There are two types of emitters. One is the pressure compensating, and other one is the non-pressure compensating. So pressure compensating means, sorry, first we will discuss about the non-pressure compensating. The non-pressure compensating dripper is when you vary the pressure, then its discharge will be varied. But pressure compensating emitter, when you vary the pressure, then discharge will remain constant. Okay. So if you are using the pressure compensating emitter, then all crops in your field will get the equal amount of water. Okay, irrespective of where um, uh, any particular plant is getting more pressure or less pressure, discharge will remain same. Okay, that's why pressure compensating emitters are generally used on uneven topography. Okay, and in the and on the plain land, these non-pressure compensating emitters are used because pressure compensating emitters are more costly in comparison to the non-pressure compensation. Okay. Now the emission uniformity. The pressure compensating emitters are capable of providing more uniformly compared to non-pressure compensating emitters. Okay, because pressure compensation will give the same discharge irrespective of the pressure change. Okay, so obviously the pressure compensate emitter will give the more uniform discharge. Okay, discharge available. When the discharge available is small, the emitter with low discharge need to be used. However, these emitters may need more time of operation. Okay, if your water resources has the less discharge, less water is there, less discharge is there, less discharge pump is used. So in that condition, you should choose the low discharge emitter. Yes, you can increase the time of irrigation time, but you should choose in that condition the low discharge emitter. Water use efficiency. Subsurface drip irrigation reduce the evaporation losses compared to the surface drip irrigation, thus resulting in more water use efficiency. This drip irrigation system is also of two types. One is the surface drip irrigation system, other one is the subsurface drip irrigation system. Surface drip irrigation system. In this, what happens? The lateral is placed on the above the soil surface, but in the subsurface drip irrigation system, lateral is placed within the soil surface. Okay. So what happens if you are placing the drip lateral above the soil surface? Then some evaporation loss may be there, but when the lateral is inside the soil surface, then there is no chances of evaporation loss. Okay. So when we talking about the water use efficiency, then we can say the subsurface drip irrigation system has the more water use efficiency. There is not so much loss of water in the subsurface drip irrigation system. The seventh is the water quality. So the emitter with more diameter of cross-sectional area need to be used for the water with heavy load of suspended solid, so that that emitter uh, can be less clogged. Okay. So if there is more suspended solid present in the water, then in that condition you should choose the emitter which has higher diameter or cross-sectional area. Now we see the hydraulic design of pipe network. Hydraulic design means it is related to the pressure and flow of the drip irrigation system. Okay. So the pipe network in the drip irrigation system consists of mainly three pipes. One is the main line, other one is the submain line, and third one is the lateral or drip line. So water under pressure flows through these pipes, and as a result, the pressure in the pipes reduces and creating the variation in pressure or pressure difference between any 2 points. The emitter discharge depends on the operating pressure available in the pipe at emitter connection and reduces with reducing pressure. Therefore, there is variation in discharge obtained by the emitters in the system, affecting the emission uniformity. Ideally, the emitter should give the same discharge at different operating pressure. So as per the principle of hydraulics, the minimum pressure variation along the lateral or along the submain can be obtained by keeping the diameter of the pipe as large as possible and length as minimum as possible. But doing this is the expensive. So on the other hand, decreasing the diameter and increasing the length, uh, though less expensive, reduces the performance of the system in terms of emission uniformity. So in order to have trade-off between the economy and efficiency, the criteria of allowing the variation in discharge of 10% amongst any two emitters in the subject is adopted. So if you are using this non-pressure compensating, means normal dripper, then in that condition you have to keep in mind that your discharge variation should not be more than 10%. This is the government recommendation. So equation for head loss due to the friction, you can calculate by this equation. HF is equal to KL Q raised to power 1.75 D raised to power minus 4.75 into F. This equation is given by Darcy-Weisbach equation. So Darcy-Weisbach equation has given this equation, and what's the meaning of this equation? When the water flows through a pipe, then there will be friction loss. Always there will be friction loss because not anything in the universe uh, is frictionless. All things have some friction. Okay, and water is not an exception. Okay? So when water flows through a pipe, then there will be some friction loss is created. Okay, so that friction loss you can calculate by this equation. Okay, and this friction loss is very important when you design the replication system. When you are calculating the pump HP. Okay, so during the calculating the pump HP, this friction loss is added in the head of the pump. Okay, so here HR is HF is the frictional head loss, and in meter K is the constant 7.89 into 10 to the power 5. L is the length of 5 in meter. Q is the total 5 flow in LPS. D is the inside 5 diameter in mm. F is the multiple outlet factor. So you can take F equal to 1. You can take F equal to 1 when there are no outlets between upstream and downstream location along the pipeline. And you can calculate F is equal to here if there is F is equal to 1. So 1 upon m plus n plus 1 upon 2n plus under root m minus 1 divided by 6n square, where m is equal to 2 and n is the number of outlets. Okay. So these are the procedure for hydraulic design. First, know the operating pressure of emitter, and after that you have to find out the reliable head loss in the lateral and submain, and third is the find out the lateral and submain discharge. Fourth is the find out the diameter and length of the lateral such that the head loss in the lateral is within allowable limit for the given layout. For this purpose, find out the head loss by Hagen-Williams or Darcy-Weisbach formula for different combinations of diameters and length, and select the suitable combination by trial and error method. Fifth, repeat the procedure for the submain also, and in the last, find out the diameter of main line so that the velocity is within the allowable limit, or find out the head loss in main for the specified diameter of the main. The length of the main is the distance of the field from the water sources. Okay. Now in the last, you can calculate the power requirement of the pump, horsepower. The horsepower requirement of the pump you can calculate by this equation. Horsepower is equal to QT into HT divided by 75 into NP, where HP is the horsepower, QT is the total discharge in the one shift or in the one field. Okay? It is expressed in liter per second. You have to keep uh, attention on this unit. So here in this formula, Q is in liter per second. HT is a total head, means head loss in the emitter plus head loss in lateral plus head loss in submain plus head loss in main line plus head loss is um, filter. Okay, so all these head loss you have to add. Okay, and here NP is the efficiency of the pump. Okay, so in this way you can calculate the horsepower. Here HT total head. How you can calculate this total head? Total head. Here it is given in this slide. Total head you can calculate by HF plus HE plus HF, where HF is the total head loss. Head loss या friction loss. Total head loss due to friction. So friction head loss कहाँ कहाँ होगा? So friction head loss in main line, friction head loss in sub main line, plus friction loss in the lateral, friction head loss in the accessories, means a valve, filter, fertigation unit. Okay, so सभी का हमें ऐड करना है. ऐड करके जितना आएगा, that will be the HF. Okay, and or HE. HE is the operating pressure head required at the emitter. Okay, the water will not flow automatically from the emitter. Some pressure, if the emitter reach at the particular pressure, then at that condition the emitter will discharge the required output. Okay. So H is the operating pressure head required at the emitter. So non-PC, non-pressure compression emitter have operating pressure generally 10 meter, 10 meter or 1 kg. Both are same, 10 meter or 1 kg. Okay. HS is the total static head. A static head means the you can say roughly if you are using the open well, then the distance between the pump inlet, okay, to the water level in the pump. That is the static head. So all these things you can add and you will get the total head. Okay. So this is all about this design of this drip irrigation system. Now this is for assignment. You can solve this assignment. Write down different criteria which affect drip irrigation design. In the first slide we have discussed about this. And what are the different steps for drip irrigation design? Okay, like inventory of the resources, peak water requirement. These are the steps for drip irrigation system. Explain different wetting pattern for the emitter. Yes, we have seen the wetting pattern for in the different soil, like in the clay soil, which type of emitter you should choose. The clay soil, sandy soil, loam soil. Okay, so we have discussed all these things in this topic. So this is all about for today's topic. Now in the now I am closing this. And length of the lateral such that the head loss in the lateral is within allowable limit for the given layout. For this purpose, find out the head loss by Hagen-Williams or Darcy-Weisbach's formula for different combinations of diameters and length, and select the suitable combination by trial and error method. Fifth, repeat the procedure for the submain also, and in the last, find out the diameter of main line so that the velocity is within the allowable limit, or find out the head loss in main for the specified diameter of the main. The length of the main is the distance of the field from the water sources. Okay. Now in the last, you can calculate the power requirement of the pump, horsepower. The horsepower requirement of the pump you can calculate by this equation. Horsepower is equal to QT into HT divided by 75 into NP, where HP is the horsepower, QT is the total discharge in the one shift or in the one field. Okay? It is expressed in liter per second. You have to keep uh, attention on this unit. So here in this formula, Q is in liter per second. HT is a total head, means head loss in the emitter plus head loss in lateral plus head loss in submain plus head loss in main line plus head loss is filter. Okay, so all these head loss you have to add. Okay, and here NP is the efficiency of the pump. Okay, so in this way you can calculate the horsepower. Here HT total head. How you can calculate this total head? Total head. Here it is given in this slide. Total head you can calculate by HF plus HE plus HF, where HF is the total head loss. Head loss या friction loss. Total head loss due to friction. So friction head loss कहाँ कहाँ होगा? So friction head loss in main line, friction head loss in sub main line, plus friction loss in the lateral, friction head loss in the accessories, means a valve, filter, fertigation unit. Okay, so सभी का हमें ऐड करना है. ऐड करके जितना आएगा, that will be the HF. Okay, and or HE. HE is the operating pressure head required at the emitter. Okay, the water will not flow automatically from the emitter. Some pressure, if the emitter reach at the particular pressure, then at that condition the emitter will discharge the required output. So it is the operating pressure head required at the emitter. So non-PC, non-pressure compressor emitter have operating pressure generally 10 meter, 10 meter or 1 kg. Both are same, 10 meter or 1 kg. Okay. HS is the total static head. A static head means the you can say roughly the if you are using the open well, then the distance between the pump inlet, okay, to the water level in the pump. That is the static head. So all these things you can add and you will get the total head. Okay. So this is all about this design of this drip irrigation system. Now this is for assignment. You can solve this assignment. Write down different criteria which affect drip irrigation design. In the first slide, we have discussed about this. And what are the different steps for drip irrigation design? Okay, like inventory of the resources, peak water requirement. These are the steps for drip irrigation system. Explain different wetting pattern for the emitter. Yes, we have seen the wetting pattern for in the different soil, like in the clay soil, which type of emitter you should choose. The clay soil, sandy soil, bone soil. Okay, so we have discussed all these things in this topic. So this is all about for today's topic. Now in the now I am closing